Hi, I'm Thibaut. Bogdan and I are both software engineers, part of the YouTube web team. YouTube.com recently launched the ability to download videos offline, capability only available on native apps until then. With this presentation, we wanted to showcase some of the APIs we leveraged to make this possible. So say you want to go offline. Why? Why would we start that whole journey of making the website work offline? Well, first, it was one of the top user requests from desktop users. Then we also observed a rise in hybrid devices that can be used both as traditional laptops and as tablets when traveling, for example. And lastly, we also wanted to improve the experience for users with a limited or intermittent internet connection. For example, people who have internet at school, but not at home. So how did we proceed? During that talk, we will present some of the aspects of the work we did to build our progressive web app. In particular, we'll talk about the service workers, the storage APIs we've used, and also how we've been handling the cases of multiple tabs. Bogdan will then cover the performance aspects from API to service worker supports on TV. Let's start with loading YouTube offline. When we started the project, the website didn't have any offline ability. If you are online when going to youtube.com, the browser would hit our web front-end and render the response. If the request failed because you were offline, you'd see the offline dino, the most popular game in the world. To handle the offline case, we introduced the service worker. So service workers are a piece of JavaScript that's controlled and installed by YouTube in the browser. The binary can handle network requests even before the site is loaded. So when a user enters YouTube in the address bar, the navigation request is sent to the service workers, which will then send a request to YouTube servers. If the request completes successfully, the browser will render it like before. If the request fails because the user is offline, the service worker can generate a fallback response and give it back to the browser. Okay, on paper it sounds easy, well documented. Let's go right. Well, before we do so, we have to note one thing. There will be a new player in town, the service worker, for every single network call that we make. To be sure we could safely introduce this change in production, we had to answer two questions. First, is it reliable? Wouldn't we risk to break the website if something went wrong there? Then, is it fast? Every time we make a request, we now have to do some extra work. Are we slowing down the general use case, the user being online, by having a service worker? Regarding reliability, we worked with many members of the web community to gather best practices. We also learned from some early bugs that we had on the website. With these, we defined some reliability principles for our service worker. First, we configure service workers to install new updates to their code as soon as possible. Then, we ensure that errors would all be logged and reported. We introduced a kill switch to remove service workers from the critical path if something went really wrong. And finally, we also upgraded our testing toolkits to enable end-to-end testing of both online and offline scenarios before each release. With reliability covered, we move to latency. So when they open YouTube, users want to see their videos as quickly as possible. We wanted to ensure that we are not penalizing them by introducing a service worker. In short, latency had to be at least neutral to launch service workers, and so offline. Getting there was quite a journey. First implementation were really negative on latency, so we iterated on a lot of experiments. We measured each network call to understand where bottlenecks were coming from. Over that time, about 2 years of experiments, browser also improved service workers' capabilities and helped us to get to latency neutral. Two things that we found really helpful to help reduce latency were one, to keep the binary size of the service worker as small as possible, around 100 kilobytes, and two, to use navigation preload. With navigation preload, when a user enters youtube.com, the browser initiates a request to our web servers immediately, as if there was no service worker. When the worker becomes ready, that initial request can then be used and returned by the service worker. For us, this gives us a really good improvement in initial load latency. All right. So with those parts covered, how does this all work today? So we have an install loop. So when the site is loaded, the browser will verify in the background if the service worker script has changed. If it has, a new version of the service worker binary will be installed in the browser. As part of that installation, the cached version of the site will be updated. The browser will download a bundle of resources, exactly like when native app do an update from an app store. So we store with the cache API, the HTML, JavaScript, CSS resources needed for the website. On the next load, if YouTube fails to respond, the service workers will return that stored response. With this, YouTube is ready to be used offline. What about in-app navigation? This is handled by the application binary, not by the service worker. So we have a client-side fallback implementation of the service that honors the request-response contract that our APIs would have. If such API fails to respond, the fallback service will generate the offline response. The rest of the application uses that fallback response and doesn't need to be adjusted. All right, now that we have an application that works online and offline, the goal is to play video. Let's see how we can store content to display it offline, and discuss a bit the storage APIs that we've used at YouTube. Web Offline requires us to store gigabyte worth of data in various types. Which API should we use? Where should we persist them in our browser? We ended up using IndexedDB and cache storage. In particular, IndexedDB allows us to use up to 60% of the disk space that's available on the machine. It's also something that's supported by most browsers that are used to access YouTube. And finally, it's also something that browser vendors are continuously investing on. IndexedDB and cache storage have their own unique features that make them suitable for different types of data. I like to pause on a great API of IndexedDB, which is the storage manager. By default, if you store data in IndexedDB, that data can be evicted by the browser without notifying the website if there is a low space pressure event. This is an issue when there is application critical data stored in the database, such as videos. Everything is wiped out and the app can become corrupt. To mitigate this, we use the persist API, which allows us to get a storage quota and manage it ourselves in case of low disk space event. For example, what we can do if there is like a low disk space event is to delete videos that have already been watched. Here is roughly how we use these APIs. Things that will be accessed and manipulated as JavaScript objects are stored in IndexedDB, and the video thumbnails and the assets for the app shell are stored with the cache API. If you use IndexedDB in production, you will likely have to handle rollbacks, and I just want to show quickly how we do that so that it's safe. Rollbacks happen when there is an issue with the version of the site that has been deployed, and you have to go back to the previous one. These rollbacks get very tricky when database schema changes are involved. Browsers do not allow the client to open a database with a lower version once it's upgraded. So the rollback release will end up having the V1 code interact with an incompatible schema, which can cause outages that are not easy to recover from. As a policy, we introduced a rollback safety stage that requires developers to introduce a buffer. During the buffer stage, you need to first update your code to be compatible with both the old and the new database schema. When the buffer stage releases, is rollback, nothing will break because it can handle both old and new. Once the buffer stage is rolled back safe, meaning that if there's an event, it comes back to that, all browsers come back to that version, we can then upgrade the database. It's not safe to upgrade because everyone will interact with the JavaScript in the buffer, which knows how to interact with the new database schema. Let's now talk about another part of the implementation that was interesting, lock API and broadcast channel. Web faces a unique challenge that's not present on native apps. You can have multiple versions of YouTube running in multiple tabs. While the IndexedDB database is shared among all these sites, each YouTube window manages application states in their own scope and memory. This brings up an interesting asynchronous state management problem. On that screenshot on the screen, we see that there is a download request that is initiated by the tab on the right and is handled by the one on the left. Both tabs display UI indicating the download progress. How does YouTube make it work? Well, the first challenge of supporting multiple tabs is that we don't want all tabs to communicate with the download server simultaneously. It can cause edge cases, such as the same video being downloaded in multiple tabs, and corruption in general of download data. So we introduced a leader election to web client. The idea is to have a distributed log, enforcing that only one leader tab can talk to the server at a given time. The leader election is a complex and continuous process. We need to spontaneously reassign the distributed log when the previous leader tab is closed or crashed. Weblog API gives us a reliable way to manage that distributed log. Every tab will send a request to compete for the log. The first tab will be granted the access. The request callback will then return a promise that's never resolved. It allows the tab to hold the log for the entire lifespan of the tab. And that log is automatically released when the tab is closed or crashes. How do we make the leader tab handle a request initiated from a secondary tab? When the download button is clicked, it adds a download task in IndexedDB. Because IndexedDB does not support notification, we use broadcast channel to tell the leader tab that a new download is queued up. The leader tab loads the task metadata from IndexedDB and uplifts all the information, such as video title, description, download information, to the browser in-memory store. And the observers to this in-memory store are triggered. The UI can be redrawn to show, for example, a video thumbnail with the progress information. One aspect we had to work on was offline detection. It was important to know when to resume downloads, for example, if the user comes back online. Initially, we relied on navigator.online, but we realized that the result was often incorrect. To work around that, we've developed a set of heuristics based on polling, navigator.online, and also checks on the result of various network response. You can define your own logic there, but our message with that slide is to take the result from navigator.online with a grain of salt. It can be wrong. Having offline support was not all. We wanted the web experience to look and feel as integrated as native apps can be. One thing we found tricky was to educate users on the availability of the website offline. When asked, many people think they simply cannot go to the youtube.com when offline, and they wouldn't even open their web browser to test. So we do all that, and basically they would be unable to watch the videos they've downloaded. To work around that issue, we've developed user education. When a user clicks on download, we show them a message telling them that they can install the YouTube app. Going through that flow installs the progressive web app. And what we do under the hood is that we capture the before install prompt when the site loads, so that we can release that event when the user clicks yes to install. That way, with the YouTube icon present on their system menu, users have a place to go when they are offline. We also worked on sharing. While many users copy and paste URLs when they have a browser, this is not possible in a progressive web app environment because there is no URL bar. And also, existing sharing destinations that work well within a browser by, for example, opening a new tab, feel weird in an app. The user expects the sharing destination to open the target app if available. So with the navigator.share API, we're becoming more like native applications, and we are allowing users to share to the applications they have installed on their computer without copying and pasting that redirect to a browser. Lastly, we're also using jump lists to allow users to go directly to the part of the application they like. You can define the shortcuts in the application manifest. So you set a URL, an icon, and a title for the shortcut. And the users will see them when they right-click on the application icon. One caveat to note here is internationalization. You cannot supply translation in the web manifest. So as a result, instead of being a static JSON file, you might have to create an action on your web server to return it so that the entry subscription, for example, is returned in the user's local. Bogdan will now talk about Cobalt.
Yeah, so I wanted to cover a few more interesting things in which we've used kind of the more complex web APIs that are available. And then one of the interesting things I wanted to touch on first is that YouTube has our own browser that we built in-house called Cobalt. Next slide. Yeah, so Cobalt is an open source fork of Chromium. that has a very minimal feature set. It's missing certain HTML tags like text area, and some of the CSS APIs like Flexbox are not available. The browser is heavily optimized to run on Living Room app, which for us is the applications that run on televisions and console hardware. Think of your Roku, your like your Xbox. These devices are oftentimes very memory and CPU constrained. The minimum requirements that we have for our OEMs are a Raspberry Pi Zero. So you can imagine how low performing some of these devices are. Cobalt allows us to offer a unified application across 10,000 plus device types by building a single web app. Go to the next slide. So because we have such a heavily constrained client, Cobalt recently announced supporting service workers. The main driving force behind this was the ability to streamline the application startup. The YouTube client here is a web app and requires downloading JS and CSS assets, as well as a number of other resources. By having a reliable cache of this data in the browser, we're able to skip these round trips and load the application much faster. This is essential for application needs to run in order to resolve OAuth and kick off the first data request. Authentication on these devices is often handled by the OS, and minimizing the work before the first request is essential to minimizing startup latency. And then another thing I wanted to touch on are some of the other web APIs that we've optimized, especially around performance. These are, go to the next slide. Mostly around the web, like the core web vitals. One of the things we've invested in recently has been optimizing specifically the LCP and FCP. Feeling more like a native app means that you have a more responsive application. And so one example that I wanted to highlight was how we progressively load the UI for the the watch page, our watch surface, where we play the videos on our mobile web application. Here we block out the player and show a block that has like a progressive degradation of UI. So we'll try and load the thumbnail if possible. If not, fall back to the first frame of the video, and then a black rectangle. This has shown like a great 4x improvement in core browser metrics, which is often tied to like the performance of your website and even SEO. Yeah, so that's just some things that I found were interesting. Thank you all for coming. We'll be at the Discord to answer any questions. Have a good day.